Okay, so now we are going to like switch gears and like talk about something other than classification. So that is what we have been, which is what we have been focusing so far, like for several weeks, right? Like so today we are going to talk about dimensionality reduction. Okay, which is an unsupervised problem. Okay, so while things like classification or regression are considered to be supervised problems, like where you have a label that you want to predict, right? Like so. Now, in this case, this is not a prediction task. So, like maybe let me first define like dimensionality reduction. Okay, more formally. Okay, so let X be some d-dimensional random vector. Okay. Our goal is to find some k which is less than d directions, okay, that captures as much as possible of the variance of x. Okay, so given some input x which is d-dimensional, okay, I would like to project this d-dimensional, let's say 100-dimensional input to some 10-dimensional vector, okay, but with a constraint. The constraint is I should prefer, like I should preserve the variance of the data as much as possible. There are a couple of questions here. Like first of all, why should I preserve the variance? What is the significance of variance? Yeah.
So you can discriminate easily between your features that are important.
Okay. But why specifically variance? Like so, is there any other property of the data that I could preserve? So I'm essentially doing dimensionality reduction here, right? So I took a high dimensional data and I'm projecting it to some low dimensions. So now, why does it need to be with the constraint that the variance of the data is preserved? If you think about it, variance kind of characterizes the data, right? Like so, it tells how spreaded the data is, like and what is the structure in the data. So if I can capture the variance as much as possible, then I'm essentially capturing the structure of the data. So then you can do classification or discrimination, whatever you want to do in this low dimensional space instead of the original high dimensional space, right? Now, what are the applications like where this idea of dimensionality reduction is useful, right? Now, there are a lot of applications. Like so, some applications that I would like to list are, first of all, feature extraction. If you want to extract a bunch of features like from high dimensional feature space, you could do dimensionality reduction, or you could do this for data visualization. Okay, let's say you have 100-dimensional data. Now, there's no way you can visualize 100-dimensional data, right? Like so, on the other hand, if I can project this 100-dimensional data to, let's say, a 3-dimensional space, capturing the variance, then I can kind of see approximately how this data would look like in 100 dimensions, right? So I can have approximate visualizations if I can do dimensionality reduction. And of course, it is also used for compression. Like if you want to reduce the dimensionality of the data, like it's some sort of lossy data compression. Okay. Now, we have already seen one example algorithm for doing dimensionality reduction. What was it? No.
Third assignment?
Sorry?
The board?
Sorry, what?
For the third assignment, when we just decide to work on most version boards?
No. Yeah.
L1?
But I think you also mentioned L1. Well, L1 is kind of like indirectly doing it by setting some of them to 0. but that has nothing to do with maintaining the variance, right? So, well, maybe it is doing something indirectly which is similar to this, but it is not exactly same. But we have seen something else like very recently. Well, there is an answer in the chat. Do you remember autoencoders? So the basic idea in autoencoder was to take an input X, project it to a low dimensional representation, and try to decode it back, right? So autoencoder is an example for dimensionality reduction algorithm. Okay, so we are going to develop some other dimensionality reduction techniques today. Okay, now to make our discussion simple, we are going to start with the 1D case, which means I'm going to take any dimensional data and project it into just one dimension. Okay, so I'm going to find the single direction, okay, that captures as much as possible of the variance of X. Is that clear? We will do one dimension and then we will generalize to like more dimensions. Okay. Now, more formally, like we are looking for some vector P, which is d-dimensional, right? Such that the norm of the P is equal to 1, so as to maximize the variance of P transpose X. Yeah.
You said P equals to what?
Okay, I haven't explained it yet. Okay, so we have some input X, which is d-dimensional, right? I'm looking for one-dimensional projection, which means I have to multiply this d-dimensional vector with another d-dimensional vector. The dot product is going to be one number, right? So that vector is going to be P. Okay. Now I'm looking for a P which has maximum variance after projection. So the variance of P transpose X has to be maximum. Okay. Now I'm adding an extra constraint here that P cannot be any vector. P has to be a norm 1 vector. Can someone tell me why should I add this extra constraint? Like, so why the norm of P should be equal to 1? Yeah.
Because you want a direction and you don't want to like scale your data.
Yes, like because a very cheap trick to increase this variance is by just magnifying P, right? I could keep on magnifying P and my variance is going to increase, right? Like, so we don't want that to happen. Like, that is not our goal. So our goal is not about the magnitude, our goal is about the direction. So by setting norm of the P to be 1, you are working in this restricted space, like where you are finding that P, which is going to give you the maximum variance. Is that clear? Now, let us derive that P, okay? So to do that, we need to define a couple of things. Let's take the original data X and let mu be the mean of this data. Mu is expected value of X, okay? Similarly, let S be the covariance of the data, okay, which is also defined as expected value of X minus mu transpose. Is that clear? Now, let us take any P, okay? So for any P belonging to R power D, now let us consider the data, the projected data P transpose X. Now, what would be the mean and variance of this projected data? Okay, so the mean of this projected data is given by expected value of P transpose X, okay, which is P transpose expected value of X, which is just mu. Okay. Similarly, the covariance or the variance of P transpose X is given by expected value of P transpose X minus P transpose mu the whole square. This is just a standard formula for variance, right? Like it's x minus mu the whole square. My x is p transpose x, my mu is p transpose mu. Is it clear? So now I can expand this. So this is expected value of p transpose x minus mu transpose p. Okay. Now we already know what is this. What is the expected value of this? It's the variance of the original data, right? So this can be written as just p transpose yes p. Is that clear? So what have I done so far? Like, so I took the original data set and I assume that mu is the mean of the original data set and s is the variance of the original data set. Then we ask this question, like if I do some projection p, then I get this new data set p transpose x. So what would be the mean and variance of this new data set? The mean of this new data set is p transpose mu, and the variance of this new data set is just p transpose sp. Okay. Now we have all the entities that we want. We can set up our optimization process. So the optimization process here, our goal is to maximize the variance of the projected data, right? So the maximize p transpose sp. Okay. Subject to the condition that norm of p is equal to 1. Is that clear? Now, another way to reformulate this is I don't want this constraint. Okay, so if it is unconstrained, it is easy to optimize. So I can remove this constraint by saying maximize, okay, for any p which is not equal to 0, p transpose sp divided by p transpose p. Okay, so I'm just normalizing it so that that constraint is taken care of. Is that clear? So any questions so far? Like, so we have just set up our dimensionality reduction program, which is to maximize the variance of this projected data set. Like, but the projection is just one dimension. Okay, so here's where we are going to use a little bit of linear algebra. So this was in your reading many weeks back. Okay, so given any matrix, okay, we can actually do a spectral decomposition of this matrix. Okay, let us take this matrix yes. Okay, so I'm going to do a spectral decomposition of this matrix X into 3 matrices. Okay, so Q del Q transpose. Okay, where this del that you are seeing here is a diagonal matrix. Okay, so this diagonal matrix will have all the eigenvalues of this matrix in the diagonal, and the Q matrix that you are seeing is actually the matrix of eigenvectors. Okay, so this Q matrix is a matrix with orthonormal row vectors, okay, which are basically the eigenvectors of this. Okay, so it is orthonormal vector, which means Q transpose is identity. Okay, now this is just a background. Okay, so now given any matrix, you can do this orthogonal, like you can do this like eigen decomposition. Okay, so we are going to do that for yes here. So I'm going to change this as max p not equal to 0, p transpose q del q transpose p divided by p transpose. I'm going to exploit this fact that q transpose is equal to I. Okay, so I'm going to put a q transpose here. Okay, it's an identity operation, so it doesn't really add anything. Is that clear? Now, let us assume that y is equal q. Let's give a name for q transpose p. Okay, so q transpose p is going to be y. Okay, so then this becomes max y not equal to 0, y transpose del y divided by y transpose y, by writing like this. Is that clear? Now, I'm going to expand this further. So max y not equal to 0. We know that This del is actually a diagonal matrix which has a bunch of eigenvalues. Let's just call them as lambda 1, lambda 2 to lambda d, and the rest is all 0. Okay. I'm going to make one assumption here, which is this eigenvalues are sorted by their magnitude. So lambda 1 is my maximum, like largest eigenvalue, and lambda d is my smallest eigenvalue. This is just an extra assumption that we are making. Okay, so this lambda vector could be like anything. So we're just assuming that lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda d. And the corresponding eigenvectors are given by u1, u2, ud. Is that clear? So now you have this y vector, and that is multiplied by a diagonal matrix, which means every component of this y vector is multiplied with one of the diagonal elements, right? So I can actually expand this whole operation. So this is going to be something like this. It's going to be lambda 1 times y1 square to lambda d times yd square. Okay, so the denominator is just y transpose y, so it is y1 square to yd square. Is that clear? Any questions so far? So I'm just doing these algebraic operations step by step, like very slowly. Now I can further write this as y not equal to 0, lambda 1 y1 square by summation over I square plus lambda 2 y2 square by summation over I square to lambda d yd square by summation over I square. Right? I just put the denominator for everyone separately. So nothing, no fancy algebraic tricks here. Now this is where we're going to use some basic properties. So you have a bunch of lambdas, and they are combined by a convex combination, right? So your combination is the weight. If you look at the weighting coefficients, they sum to 1. So you have a convex combination of a bunch of values, and you are interested in finding the max. Okay. Now there is an upper bound for this. Okay. So this is going to be always less than or equal to lambda 1. You can verify this by writing some simple Python programs like where you give a bunch of values and you do weighted average and see what is the maximum value. The maximum cannot be more than lambda 1 because this is a convex combination. Okay. Now, when will this be exactly equal to lambda 1? Yeah.
When y has 0 everywhere except for the first component.
Yes. When y has 0 everywhere except for the first one, right? So now, or in other words, like when y is equal to E1, okay, E1 is an I vector. Like if you have done, if you have seen this in like some matrix course, like or linear algebra courses, like so E1 is basically a fancy way of saying 1, 0, 0, 0, something like this. So E2 is 0, 1, 0, 0, 0. Okay, so when y is equal to E1, then the maximum value that we could get is going to be lambda 1. Okay, now what does that mean? So if y is equal to E1, then that just means my z is going to be q times E1, okay, which is nothing but U1. Is it clear? So if I just substitute that I want y to be E1 in my previous equations, like so I would get q times E1. Now q we know is an orthonormal like row vectors of basically the eigenvectors, right? Like so this basically says you pick the first eigenvector, which is U1. Okay. So now we know that the first eigenvalue was actually the largest eigenvalue. which means the first eigenvector was the corresponding eigenvector to the largest eigenvalue, right? Now, so this whole optimization process tells us that if you want to take the data and project it to just one dimension without losing too much variance, then the best thing to do is to take the data, compute the covariance of the data, and just pick the first eigenvector of this covariance matrix, okay, as your P. Is that clear? Now, this first eigenvector, right? First eigenvector of the covariance of X, right? So we're going to call this as the first principal component. Okay. Now I can generalize this derivation. Like, so if I want to project my data into k dimensions instead of just one dimension, all I have to do is to pick my first k principal components. Is that clear? So this idea of using the principal components to project your data is called principal component analysis. Or PCA. Okay, so here is the general procedure for PCA. Maybe I'll write it in the next page. The general procedure for PCA. So first, you compute the mu of the data and also yes, the covariance of the data X. Okay, so then the next step, you compute top k eigenvectors like u1 to uk of yes. Okay, so then you project X to some P transpose X, okay, where the P transpose is actually a K cross D matrix, where the rows are U1 to UK. You take the principal components, put them together, that is your projection matrix. Is that clear? It is very simple to implement. You can implement it from scratch by yourself. Like if you're using something like NumPy, it is going to give you the principal components like by just doing like simple value decomposition. Yeah.
Is there any sort of expensive things to do to calculate the matrix of eigenvalues, since the objective was already at first dimensionality reduction, because we add features and so on?
Okay, that's a good question. So isn't it computationally expensive? Now, there are a few things to consider here. Like, so first of all, this is not an iterative algorithm, right? Like, so this is just one step. Like, so if you want to do dimensionality reduction, like let's say you have some time, you have compute, you can do this. Now, like I did not tell you how to compute the come up with the eigenvector, right? Like, so there is a lot of work in the literature on like efficient ways of computing the eigenvectors, like or iterative ways of computing the eigenvectors. Like you can use any standard package which is doing this for you. Okay. Now, a quick question. So can we use PCA for classification? So do you think after doing PCA, I do a classification, the problem is going to be similar or easier? Yeah.
No, unless like your X feature is literally like your classification.
Yeah, it depends, right? Like, so for example, let us take an example. So let's say I have a data set which is looking like this. Okay, I have a data set like this. And I want to do principal component analysis with just one dimension. This is already a 2D data. I'm going to project it to one dimension. Can somebody guess what would be the principal component for this data? So that is the direction which has maximum variance, right? So you can intuitively tell what is the principal component here. So what is the principal component here? Okay, let me give you two options. Is it this or this? 1 or 2? How many of you think it is 1? People in the chat, you can answer in chat, like I will see your answers. How many of you think it is 1? Okay, how many of you think it is 2? Okay, so it's actually 2, right? Like, so let me remove these things together again. So any direction in which the data has huge spread, okay, that is a very approximate way of saying that. Like, so in this case, it is going to be something like this. Now, this first, I project all the data to this first principal component. Okay, I project everything to this data, this one vector. Now, this has actually made the problem worse, right? Like, so initially I had a perfect linearly separable problem. By projecting it to the first principal component, I have mixed all the data together. Like, so now I cannot find a line which, like, find a threshold which cuts these two data sets. Okay, now that is bad, but it is kind of understandable here because PCA is an unsupervised algorithm, right? So there is nowhere in the principal component analysis we added the Y information. We just looked at X, right? Like, so it doesn't matter what is the class label, like in PCA. Now, how can I use a dimensionality reduction algorithm like PCA, but in such a way that the reduced dimensions that I get is also useful for the classification problem in hand, right? Like, so that requires development of supervised versions of PCA. Okay, so now we are going to do one such algorithm, but before that, so let's take the same example. Now, which direction do you think we should be projecting our data if we want good separation? Yeah. So the one which is like this, right? So if I project my data to this line, then all the cross will get projected here. All the circles will get projected here. I actually have a perfect division of data, right? So basically, we want to find the projection, okay, that maximizes the class separation. Okay, yeah.
We can do the orthogonal to the PCA.
Okay. Being orthogonal to PCA would help you in this particular example, but I can construct another example where being orthogonal to PCA will also not help. Okay, that is a temporary solution for this example. Like, but we are looking for something which would work for any example. But that's a good guess. Okay, now we're going to develop like a variant which is going to do this for us. Like, so to do that, like let us assume that we are working with two class problem. Okay, when you have two classes, let us say there's class C1 and class C2, and there are n1 data points for class C1 and n2 data points for class C2. Is that clear? So now we are going to separately define the mean and variance for these data, like two classes. Okay, so let M1 be the mean for class 1. Okay, so it is defined as 1 over n1 summation over n belonging to class 1 x of n. I take a bunch of x's which are all from class 1 and I compute the sample average, that is my mean M1. Similarly, my M2 is going to be 1 over n2 summation n belonging to C2 x. Is that clear? Now, one heuristic to come up with a supervised version of PCA is to make sure that the mean of these two data sets, like two classes, is as far as possible, right? So I can choose some W, just like how we had P in principal computer analysis. Let's have some vector W, so as to maximize W transpose M2 minus W transpose M1. I want this difference to be maximum. Is that clear? Again, we are going to have the same problem as PCA. Like we can actually make this difference maximum by just magnifying W. We don't want that to happen. So we're going to add a constraint that W now should be equal to 1. Okay. So here is my new optimization problem. Like so maximize W transpose M2 minus W transpose M1 subject to the constraint that W transpose W is equal to 1. Is that clear? Now, we have already seen how to solve constraint optimization problems like in SVMs and other places, right? Like, so I can take a Lagrangian formulation for this, differentiate it to 0, I'll get a solution. So I'm going to come up with the Lagrangian formulation here, which is basically W transpose M2 minus W transpose M1 plus lambda times W transpose W minus 1. I took the constraint, which is W transpose W is equal to 1, so it becomes W transpose W minus 1 is equal to 0. I add a lambda, which is my Lagrangian multiplier, right? So another way to, okay, sorry. Okay, we are going to lose the screen. Okay, we lost the screen. Let's just wait for a few seconds for the screen to come back. This is a big problem with this camera. Okay, so while we are waiting for the screen, like I will just write the next step. So, which is very simple, like I'm just taking the W transpose outside. Okay, the screen is back. Okay, so this is my L. Okay, now I need to find the W, which means I have to differentiate this with respect to W and set it to 0, right? So let me copy this L to the next page. Okay, so now dou L by dou W. I'm differentiating with respect to W. So this becomes M2 minus M1 plus 2 lambda W is equal to 0. Okay, which means W is equal to minus 1 over 2 lambda times M2 minus M1. Is that clear? So we only care about the direction, not the magnitude, right? So the scalars doesn't matter. So W should be proportional to M2 minus M1. So this is a very simple algorithm. So this algorithm tells you that you compute the mean of the first class, compute the mean of the second class. Now a line connecting these two means is the data projection, right? So M2 minus M1 is an equation for a line connecting the means of these two data sets. Okay. Now let us see if this is, it looks reasonable, right? Like, so now you want to make sure that like two things are well separated. Okay. So now let us see how this works. So here is an example. Okay. So this is, okay, let me see if I can highlight things. So this is the mean for red class. And this is the mean for blue class. Okay. So you take these two means, you connect them together. So that is the line of projection. Now I have projected all my data here, and you can see that there is actually some mismatches, right? Like, so there is some blue and red classes projected together, right? Like, so now this should not happen. But is there another line that you can think of here which would have perfect classification? But I know it's very difficult to tell what is the angle, but is there another line that you think we can draw which is going to give us perfect classification? Yes, right? So like, for example, like if I draw something like this, this is going to put all these things here, it's going to put all these things here. So there is actually a perfect division, right? So how do I find this line instead of the simple M2 minus M1 line? Now, first of all, why is this happening? Right? So the main reason why you see this like mixed behavior in between is because the data that you're seeing here for blue and red classes, right? Like, so they don't have diagonal covariance. So they vary in different directions, like for themselves. So it is not enough to just consider the mean of the classes. You should also see like what is the direction in which the data is varying. Okay. Now you want to maximize the separation like between the means, but at the same time, you want to minimize the variance within the data. You want to shrink the data when you're projecting, like to one, as close as possible to the mean, so that they get separated out. Is that clear? Now, so that is the improvement to this algorithm that we have seen. Okay, so this improvement was proposed by Fisher. Maybe the spelling is wrong. Okay, so this algorithm that we are going to see now is called Fisher's linear discriminant analysis. Okay, so let us not worry about the name of the algorithm, because LDA is one of the most overloaded in machine learning. So it means sometimes Fisher's linear discriminant analysis. Sometimes it actually means the Gaussian discriminant analysis, GDA, that we have seen. Okay, and sometimes it also means latent Dirichlet allocation, which is another famous machine learning algorithm, like which has the same abbreviation. So it is really confusing. Like, let's not worry about what is the name. Okay, but what matters is the problem, optimization setup. So we are going to consider within class variances, and we are going to minimize the within class variances. Okay, now for each data set, let us consider the within class variance, sk square, to be summation over n belonging to ck, w transpose xn minus w transpose mk, the whole square. So this is for class k. When you have two classes, the total within class variance is given by s1 square plus s2 square. Is that clear? Now here is my new optimization problem. Okay, so I'm going to maximize w transpose m2 minus w transpose m1 the whole square, okay, divided by s1 square plus s2 square. Okay, so this is a bit different from our previous objective. The previous objective was just to maximize w transpose m2 minus w transpose m1 the whole, just the linear version, right? So it doesn't really matter that I add square, like they are both going to have same solution. But what matters is the denominator. So I want to maximize 1 by s1 square plus s2 square, which means I want to minimize s1 square plus s2 square. Okay, so I have like the goal here is to find that particular line which maximizes the mean between the two classes, at the same time minimizes the variance within the classes. Is that clear? Any question about this? Okay, so now let us see how to. Okay, so now let us see how to maximize this. Okay, so let me move to the next page. Let's just consider the numerator first. So the numerator was w transpose m2 minus w transpose m1 the whole square, right? So I can actually rewrite this as w transpose m2 minus m1 the whole square. Okay, I think we lost the screen. Okay, now this is basically w transpose m2 minus m1, m2 minus m1 transpose w, right? Now we know what is m2 minus m1. So it's between class covariance matrix. Okay, so this is basically w transpose sbw, okay, where sb is the between class covariance matrix. Is that clear? So this is for our numerator. Now similarly, let us also simplify our denominator. Our denominator was s1 square plus s2 square, right? So this is basically summation over n belonging to c1, W transpose xn minus m1 the whole square. This is the variance for first class, plus summation over k belonging to C2, W transpose xk minus m2 the whole square. Is it clear? I can actually expand it similarly. So summation over n belonging to C1, W transpose xn minus m1, xn minus m1 transpose W, plus summation over k belonging to C2, W transpose xk minus m2, xk minus m2 transpose W. Okay. I'm going to put all of this into one notation. So we're just going to call the whole thing as W transpose SW W. Okay, where SW is a shorthand notation for summation over n belonging to C1, xn minus m1 xn minus m1 transpose, okay, plus summation over k belonging to C2, xk minus m2, xk minus m2 transpose. Okay, so I took all these summation things, like I put them as one notation, like so that it is actually easy for us to see the whole thing in one equation. Okay, so now the whole thing can be rewritten as W transpose SB W divided by W transpose SWW. Okay, now this is easy to differentiate and set it to 0. So what I have done here is, like, I have two terms. The numerator is about the between class variance. Okay, the denominator is about the within class variance. I want the between class variance to be larger, like I want them to be as far as away as possible. At the same time, I want the within class variance to be smaller. Is that clear? Okay, so now I can actually differentiate this and set it to 0. Differentiate with respect to W and set it to 0. So we are differentiating with respect to W. So this is U by V, right? So what is the differentiation function for U by V? Basic calculus, yeah?
U squared minus V squared.
So it's V du minus
V
V.
minus U V squared. U there is
Okay, maybe we are talking about the same thing, like so, but a simple way, whenever you have U by V, the differentiation is given by V du minus U dV. Okay, so which means V, okay, so this is W, sorry, W transpose, okay, I'm not sure if it is V du or U dV.
That's a denominator.
Sorry?
That's a denominator. By V squared.
yes.
Okay. Oh yeah. Okay. Okay. This is U by V. Okay.
It's you.
Okay. Okay. So I think I messed up.
I think that was right, divided by V squared.
No, I think it is V du minus U dV by V squared.
Exactly, that's what you wrote.
No, I wrote U dV. So,
Okay.
so V du minus U dV by V squared. Is that right? No. I think it is U dV minus V du. Okay. Can somebody verify whether if this is U dV minus V du by V square?
It's video.
It is V du, so I was right, but then maybe then some, okay. Okay, so then I think I messed up with the signs in the note, but the good thing is the signs doesn't matter much here. Okay, so for this equation, so it is V du, right?
Yeah.
V du minus U dV by V square, okay. but the signs in the notes are a little bit, I think it's swapped, but it doesn't matter because we're equating it to 0. Okay, so W transpose SBW, SWW. So like I kept the first U as such, I differentiated the other one, minus W transpose SWW, SBW is equal to 0. Okay, I think if I actually apply the equation, it has to be, the signs should be different, but it doesn't matter here, like so, because we can just equate these two things in opposite directions. So W transpose SBW times SWW is equal to W transpose SWW, SBW. Okay, now here is a simplification. We don't care about the magnitude, we only care about the direction, right? Now this is a scalar, this is a scalar, so we can just ignore them. Okay, so then you have SWW is equal to SBW. Okay, now we also know that SB is given by M2 minus M1, M2 minus M1 transpose, right? Like that is a between class variance. So I can actually use this and say that SWW is actually proportional to M2 minus M1. Is that right? You only care about the direction. So like we can go for proportional. It's proportional to M2 minus M1. So W is actually proportional to SW inverse M2 minus M1. Is that fine? Now this is my Fisher's LDA. So there is only one difference between my previous solution and this solution. The previous solution was to find the line which connects M2 and M1, M2 minus M1, right? Now I'm adding a constraint that I'm dividing that by the within class variance. Is that clear? Now this is going to correct the mistake from the previous algorithm. So here is the same example, but with Fisher's LDA. Okay, so now you can see that in this case, you found this line which is not just connecting these two. Like if it is connecting these two, like it will be like this, right? Like so, you are adjusting the line based on the covariances of the data, and like the within class variance of the data, and like you actually have, in this case, a perfect classifier. Is that fine? Now, there is one small missing piece here though. So Fisher's LDA is still not a classification algorithm. Okay, so this LDA algorithm that we have seen is just a dimensionality reduction algorithm. It is not giving us the classifier, it is only giving you the projection dimension, right? Like so, now you have to construct the classifier. Now it is actually very easy to construct the classifier here. Like so, what you have to do is like have a threshold and tune this threshold by using the training set. Like you put the threshold here, you see what is the error. Then you just keep changing the threshold. At this point, the threshold gives you 0 error in training data, so you have solved the problem. Is that clear? Any question? Okay, so now I want to make some connection with whatever we have seen previously. Okay, so like we have seen autoencoders in the past, right? Like so if you think about autoencoders, they are actually connected to the principal component analysis algorithm. Like so, in the sense, let's say you have 100-dimensional data and you're finding 10-dimensional projection, one by using Pca and another 10-dimensional projection by using autoencoder. Okay. In fact, when you have a linear autoencoder, like you can show that these 10 dimensions, right? They are kind of same. So the projection that the autoencoder is learning is going to span the same subspace that your Pca algorithm is finding. Okay. However, there is no guarantee that each unit is by the same order, like because we don't have that constraint in autoencoder. Okay. Now, if you think about it in this way, the connection between Pca and autoencoder is a very efficient way to come up with non-linear Pca algorithms, right? Like, so Pca is a linear algorithm. Now in autoencoder, you add a sigmoid or tanh or ReLU to the hidden layer, you actually get a non-linear version of Pca. Okay. There is also another advantage of doing autoencoder. So as he rightly pointed out in the beginning, sometimes you cannot do Pca, like the data is too large, like so you cannot compute the inverse and so on, right? Like, so in those situations, you can still do autoencoder. Autoencoder is just a gradient descent algorithm. It might be faster and might converge to the same solution, like without all the technical difficulties. Okay, so I think by next week, hopefully, like, so we will also see another way to make Pca nonlinear. Okay, so but for today we will stop here. I think we are stopping a bit early, but it's okay. So any questions? I thought we should stop at 25, then I realized it's 35. Any questions so far? Let me see if there are any questions in the chat. Okay, so there is a question on, is there any exercise for the exam? So I'm going to release the previous year exam paper today, so that will be a good starting point. Yeah.
You said that we find the threshold, and when we have zero error for all the training data, we have solved the problem. Does that mean that in unsupervised learning there is no validation and testing set?
Oh, okay. So that part is a supervised task, right? Like, so in the case of unsupervised learning, like, so for example, like when you want to do just Pca or LDA, there is no notion of training or validation or test. It is the data that you have, and you are doing some analysis with the data, right? Like, so there is no train test kind of things in unsupervised learning. Like, so, however, like once you have the components, then when you want to do classification, then you will start thinking about what is your training set, what is your validation set, and so on.
I'm not sure I get to that.
So if you want to do LDA for classification, so then you will have train valid test splits. So you'll take the training set, you will learn this representation, and then you do the thresholding and stuff. But if you are not doing any classification, like if you are just interested in data compression, then there is no question of training or validation. Yeah.
So, unsupervised learning, are there any metrics to measure if we are doing something meaningful?
Okay, that's a very deep question. So how do we know that we are doing something good with unsupervised learning, like when there is no validation or test, right? So usually it is very difficult, like, so evaluating unsupervised learning algorithms, like, so like for example, let's take dimensionality reduction. So how would I measure that this is a good dimensionality reduction algorithm? So it is not the usual accuracy or precision, like, but in the it is case by case. For classification, for all the classification, there is only one metric, right? Like, it is not the case for unsupervised learning. Like in the case of dimensionality reduction, like for example, how much is the loss in compression? Like that is your metric. You have an algorithm which has, let's say, 20% loss. If I come up with an algorithm which has 15% loss, then my algorithm is a better algorithm than yours, right? Like, so, so it depends on the problem. So. Okay, so, okay, probably we can stop here. And as usual, like it's my office hours after this. Like, so if you have any questions, you can come talk to me. But work on your Kaggle competition. Like, try to make your submissions. So, thank you.